So now we're up to writing specific electron configurations for the elements, and the method it's only up to z equals 36, so only up to this point over here. And the method I recommend is, the other method I'll show on the next slide, is to just follow along this line. So this is the S block, the P block, and the D block. And the only trick is you need to know it goes from 4s to 3D. And so you just read along these lines, and then you'll get this order 1s2, 2s2. And then it goes over here to 2p6, which is here. And then you go back down to 3s2, 3p6 across here. And then you'll have 4s2, 3d10. So where we go, 4s2, 3d10, 4p6. So this is the 4. And then you're done. And so that's all the ones you have to do. You just have to work out which element it is and just count up to there and then stop. Okay, so the other method, which I used to teach, which I don't teach anymore, is just to increase these as you go across. And it doesn't really matter about here because you're never going to get this far down. And then you do a diagonal and you'll still get this same basic template to be able to work out what they are. Don't recommend that, but we need to learn how to fill in the orbitals as well. And so the first one's the Aufbau principle, and so which is what I just said before. You start here and then you move your way down, so everything's in the ground state basically, and then so just following this order as this template shows, and as I showed here, remembering that's a drop to a 3D and then back up to the 4p again over here. The second rule is Hund's rule, and that's basically when you get to one of these orbital blocks, you have to put one electron in each of the x, y, z, and each one of these ones first before you add the ones in opposite directions. So you've got to fill up so it's nice and even around the nucleus before you throw a second one in there. And for this one, it's like 1, 2, 3, 4, 5 before you start doing the second ones, 1, 2, 3, 4, 5 in the Ds. And same with the S's. That's pretty obvious though, because there's only one orbital, so one up then one down. Okay, so that's Hund's rule. And the last rule is the Pauli exclusion principle, in that to balance each other out. Just like a north pole and a south pole, they like to have less stress, and you should store your magnets like this, otherwise you cause stress and it destroys them. If you store them like north to north and there's all this repulsion going on, and south to south. So the electrons, that will flip anyway if you put these two magnets together just like the electrons do, so you need to put them in opposite direction when you put the second one in there. And so when you're doing ions, just take a note of how many are gained or lost. So that's lost an electron. So when you write out the proper electron configuration first and then just take one away if you had to do that. This one you need to add 2. So, and this one has gained an electron 2 electrons, so you need to add 2. So there's a 2p4 to 2p6. So that's how you do the electron configurations for ions. The condensed forms you also need to know, so you don't have to write all this extra stuff. So for instance, if you're doing titanium, you can just go to the nearest noble gas and put a square brackets around it. And so that is 1s2, 2s2, 2p6, 3s2, 3p6. You don't have to write that, what I just said, which was that. You can just do the argon, and then you just do the little bit extras in front. And it doesn't matter if you put the D or the S first, because they're so close together they overlap and it doesn't matter. So you can put either first. And so you can do that for all the noble gases. Just find where the base is, whatever it's closest to. So you could do it for carbon as well. Just write helium and then just write 2s2, 2p2. All right? So you don't have to write the full. Make sure you know in the question whether they've asked for full electron configuration or the condensed form. So the condensed form has the noble gas there to shorthand to make it quicker. So orbital diagrams, following the Hund's rule. Hopefully they won't ask you to draw them in, but they could. Hopefully they have a template there for you to fill in. And I'm just going to let you have a go at that, or maybe the teacher can do the first 1 or 2 in class. I've got this down here to help you. And then you can just pause it and look through the answers and see how you go. So I'll just flick through the answers here with enough time to pause. All right, now finally is the exceptions. There are 3 exceptions based on these 3 concepts here. So first of all, the 4s and the 3d, they're so close together that they overlap. So there's no real difference in electrons going in between the two. The next is, as you saw from the demonstration at the front of the video, that they like to be evenly distributed around the nucleus. And mutual repulsion is a thing. So there is repulsion in having 2 electrons close to each other, and so they like to avoid that if possible. All right, and so here you can see that the how close they are. The 3D, sorry, the 4s and the 3D 4s there, and the 3D, they are very close to each other. Okay, so these are the exceptions. The first one is chromium. And so instead of having mutual repulsion and having this 4s2 and 3d4, there's mutual repulsion there. So all it has to do is move out, and then you don't have any mutual repulsion. On top of that, you have a completely half-filled subshell, which has some element of stability to it, and symmetry to it. So you need to know these exceptions. They're commonly tested on. So it's not 4s2, 3d4, chromium's 4s1, 3d5. And in a similar notion, you can have a full D shell or a full S shell. And they prefer to have a full D shell rather than a full S shell. And so the electron moves up here. So instead of being 4s2, 3d9, it's 4s1, 3d, 3d10. Okay? And the last rule you need to know is when you're doing ions here, take the electrons away from the 4s2s first, which explains why all the transition metals like to be 2+. And if you don't know what charge they are, and someone's forgot to say, call it 2+. All right? So make sure you know those 3 exceptions to the rule. It's especially tricky when you're doing the ions. Make sure you draw out the correct transition metal structure first, and especially if it's the exceptions, because that can be very tricky. Then take the 4s away, because otherwise you won't get the correct configuration.